Scale-less linear encoder. SensorLab. Features of the Motorcoder. Principle of the Motorcoder. Drive a linear motor with a Mitsubishi servo and a Panasonic servo. Repeatability of the Motorcoder is less than plus and minus 10 micrometer. Maximum speed of the Motorcoder is over 3 meters per second. Since the Motorcoder is an absolute position linear encoder, there is no need for magnetic pole detection. Features of the Motorcoder.
Resolution of 1 micrometer, maximum speed of 3 meters per second or more. Sensing linear motor magnets instead of scales. Compatible with Mitsubishi and Panasonic servos. Ultra-long distance absolute position linear encoder with a battery of over 10 meters.
Principle of the Motorcoder. This video shows how to drive a linear motor, using a linear encoder to which multiple Hall sensors are applied without a scale. This linear encoder without a scale can be a good alternative solution in cases where it is difficult to apply a typical linear encoder with a scale. By using the linear encoder without scale, the linear motor can be controlled without performing a phasing operation to search for an electric angle. If you connect the battery to it, it senses the absolute position for the full stroke. Whereas a typical linear encoder is composed of a linear scale and an encoder head, this linear encoder without a scale senses the absolute position using Hall sensors and the magnet track of the linear motor. The principle of sensing an accurate position without scale is as follows. The accurate position is calculated by sensing the magnetic flux density of the permanent magnet track of the linear motor with a number of Hall sensors. Hall sensors output sine and cosine analog signals, as Lissajous waveform, by sensing the magnetic flux density of the north and south poles of the permanent magnet track. After calculating the accurate position using the high-resolution interpolator, the linear encoder without scale is transmitted accurate absolute position data to the servo drive through serial communication. Therefore, the linear motor can be controlled immediately even when the power is turned on, without the initial homing operation. As shown in the video, it is easy to use in combination with Mitsubishi servo drive and PLC, and it is very strong against noise by applying dedicated serial communication. In applications that require long-distance transport such as logistics systems, the linear encoder without a scale is applied because precision assembly or processing is not required. And because there is no scale, damage to the scale caused by dust or foreign substances or malfunction of the linear encoder is fundamentally prevented. Drive a linear motor with a Mitsubishi servo and a Panasonic servo.
The Motorcoder has no scale, so it is a linear position sensor suitable for long-distance transportation, logistics systems, and point position control rather than sub-micrometer precision control or constant speed control. I measured and saved the actual speed and the command speed using a Panasonic drive as shown in this graph. You can see that it follows the command speed of 2 meters per second well. The velocity ripple is about plus minus 17%, and the settling time, which is the position control delay time, is about 49 milliseconds. Settling time may vary depending on the load and tuning. The precision of position control is plus or minus 10 micrometers. Now, I will control the linear motor under the conditions that the command speed is 100, 300, 500, 1000, 1500, and 2000 millimeters per second. Acceleration and deceleration times are the same at 0.1 seconds. The test equipment is a Panasonic drive, a linear motor, and the Motorcoder. The resolution is 0.732 micrometers and the moving distance is approximately 307 millimeters with 420,000 counts. First, this is the video seen from above when the command speed was 100 millimeters per second. I will show you the driving video seen from the side and the speed graph saved from the Panasonic drive. The left y-axis and green line are the actual speed sensed by the Motorcoder, and the pink line is the command speed. The right y-axis and red line are the movement counts. If you look at the cursor in the graph, the settling time, which is the delay time during position control, is about 39 milliseconds. Speed ripple is plus minus 13%. Second, this is the video seen from above when the command speed is 300 millimeters per second. I will show you the driving video scene from the side in the speed graph. If you look at the cursor in the graph, the settling time is about 63 milliseconds. Speed ripple is plus minus 8.2%. Third, this is the video scene from above when the command speed was 500 millimeters per second. I will show you the driving video scene from the side in the speed graph. If you look at the cursor in the graph, the settling time, which is the delay time during position control, is about 49 milliseconds. Speed ripple is plus minus 9%. Fourth, this is the video scene from above when the command speed was 1000 millimeters per second. Because the moving distance is short, the acceleration is high, so it feels quite fast. I will show you the driving video scene from the side in the speed graph. If you look at the cursor in the graph, the settling time, which is the delay time during position control, is about 47 milliseconds. Speed ripple is plus minus 14%. Because I tuned it to suit position control for fast transfer, the command speed is faster, but the settling time is similar, but the speed ripple increases. If I tune to a smooth motion, the settling time increases and the speed ripple decreases. Fifth, this is the video scene from above when the command speed was 1500 millimeters per second. I will show you the driving video scene from the side in the speed graph. If you look at the cursor in the graph, the settling time is about 45 milliseconds. Speed ripple is plus minus 15%. Sixth, this is the video scene from above when the command speed was 2000 millimeters per second. If you look at the cursor in the graph, the settling time is about 49 milliseconds. Speed ripple is plus minus 17%. When the speed is increased from 100 millimeters per second to 2 meters per second, the delay time during position control is up to 63 milliseconds. Of course, there is no load, but it has similar characteristics to position control using an optical encoder.
Repeatability of the motorcoder is less than plus and minus 10 micrometer.
I will explain the equipment configuration for repeatability measurement. I use a linear motor, 2 Mitsubishi servo drives and a PLC. I mounted the motorcoder, a red PCB using Hall sensors, in front of the coil unit, to face the permanent magnet unit in the linear motor. I additionally attached an optical linear encoder head and scale to the side of the coil unit as a reference sensor for comparison. The optical linear encoder outputs an incremental signal, which is input to the first Mitsubishi servo drive, and the position data sensed by the motorcoder is input to the second Mitsubishi servo drive through serial communication. 2 Mitsubishi servo drives are connected to a Mitsubishi PLC. To measure repeatability, I control the linear motor with a second servo drive through a Mitsubishi PLC. I simultaneously receive and save position data from 2 servo drives using PLC. As shown in the graph, I moved and stopped the linear motor 7 times by 150 mm from the origin, then moved it in the reverse direction again with the same motion. I repeated this round-trip operation a total of 10 sets to save the position data of the optical linear encoder and the motorcoder, and compared the position data of the two sensors when the linear motor completely stopped. According to the measurement results, the bidirectional repeatability of the motorcoder compared to an optical encoder is 11 micrometers, that is, plus or minus 6 micrometers. Please refer to the first video below for comparative results on repeatability and position accuracy. The difference between the position data measured with an optical linear encoder and the position data measured with the motorcoder is shown in the following graph. I defined the difference in position between the optical encoder and the motorcoder as the error of the motorcoder, because the optical encoder is more accurate than the motorcoder. The maximum error of the motorcoder is about 500 micrometers, and since the permanent magnets of a linear motor cannot be attached at completely equal intervals, the difference inevitably occurs. In other words, since the motorcoder uses a permanent magnet array arranged in a row and a linear motor as a scale, position accuracy error occurs due to permanent magnet attachment error. However, you can see that the repeatability of the motorcoder, that is, the repetitive deviation of the error of the motorcoder, is plus or minus 6 micrometers, which is relatively very precise compared to the position accuracy. If you zoom in on the graph at 150 and 300 millimeters, it looks like the following graph. When repeated 10 times in both directions, you can see that the deviation in the error of the motorcoder is up to 11 micrometers. I will show you the graphs for forward and reverse repeatability of the motorcoder in turn. You can see that the two graphs are similar in that the error of the motorcoder does not increase even if the direction changes. From this, we can see that the main cause of repeatability is the interpolation error caused by the large pole pair pitch of magnet. The motorcoder's accuracy is over 500 micrometers, but its repeatability is about plus or minus 6 micrometers. It's not accurate, but it's precise.
Maximum speed of the motorcoder is over 3 meters per second.
I can drive a linear motor using a scale-free motorcoder and a Mitsubishi servo drive. I can use a Mitsubishi servo drive or a Panasonic servo drive. For comparison, I installed the motorcoder for control and an optical linear encoder for measurement. The optical linear encoder outputs an incremental signal, which is input to the first Mitsubishi servo drive, and the position data sensed by the motorcoder is input to the second Mitsubishi servo drive through serial communication. Two servo drives are connected to a Mitsubishi PLC. To measure speed, I control the linear motor a second servo drive through a PLC using the motorcoder. I simultaneously receive and save position data from two sensors and two servo drives using PLC. I drive a linear motor with a travel distance of 1 meter, at speeds of 1, 2, and 3 meters per second. First, I drive a linear motor at a maximum speed of 1 meter per second. For a detailed comparison, I saved the position data received from the two sensors and viewed it on a graph. The x-axis is time, and one division interval is 150 milliseconds. The y-axis is position and speed. The green line is the position of the motorcoder, and the pink line is the position of the optical linear encoder. The blue line is the motorcoder speed, and the red line is the optical linear encoder speed. Since the motorcoder resolution was about 0.7 micrometers and the optical encoder resolution was 1 micrometer, the motorcoder moved by about 1.4 million counts, and the optical linear encoder moved by 1 million counts. Looking at the red and blue lines, you can see that the linear motor operated at a speed of 1 meter per second. Secondly, I drive a linear motor with a speed of 2 meters per second. I displayed position and speed in the graph. Looking at the blue and red lines, you can see that the linear motor was running at 2 meters per second. When the linear motor was driven at 1 meter per second, it started running at about 150 milliseconds and stopped at about 1.2 seconds, but when driven at 2 meters per second, it stopped at about 750 milliseconds. Finally, I drive a linear motor with a speed of 3 meters per second. If you look at the speed graph, you can see that the linear motor was running well at 3 meters per second. A linear motor started running at about 150 milliseconds and stopped at about 600 milliseconds. Because it is based on serial communication, the motorcoder has no maximum speed limit and is highly resistant to noise, making it suitable for long-distance transport.
Since the motorcoder is an absolute position linear encoder, There is no need for magnetic pole detection.
When using Mitsubishi or Panasonic servos and incremental encoders, you may have had the inconvenience of detecting magnetic poles every time you turn on the power. In particular, magnetic pole detection is often not performed well in heavy loads or gantry-type stages. If magnetic pole detection is not performed well, noise and vibration increase, and the load increases during motor operation. The Motorcoder uses the permanent magnet of a linear motor as a scale without a separate scale. When manufacturing a linear motor system, if magnetic pole detection is performed once in a no-load state, the user no longer needs to detect magnetic poles. In summary, I will show a short video of driving a linear motor without detecting magnetic poles after turning on the power using a Mitsubishi servo. I turn off the servo drive. Communication was lost in the program and I quit the program. I turn on the servo drive and rerun the program. I run a test drive without magnetic pole detection. I move the linear motor 300,000 counts at 300 mm per second speed. In this way, even when the power is turned off and on, the linear motor can be driven immediately without magnetic pole detection. Why should you do magnetic pole detection? To briefly explain, magnetic pole detection is a function in which the servo drive detects and stores the deviation in the relative positions of the linear motor coil and linear encoder. If you don't do this, you won't be able to control the linear motor. In general, when using an incremental encoder, a magnetic pole is detected every time the servo is turned on and off. You may ask, this is usually not necessary for servo motors. Magnetic pole detection must also be performed on servo motors. However, since it is only performed once when manufacturing a servo motor, users use it without detecting magnetic poles. If you look at the Mitsubishi manual, it says that the rotary servo motor has magnetic pole detection completed at the time of manufacture, so you do not need to do it. Magnetic pole detection is necessary when you use linear servo motors. In the manual, magnetic pole detection may not be performed if you use an absolute position linear encoder. The Motorcoder senses the absolute position of the coils and magnets even without connecting the battery, so the user does not need to detect magnetic poles. In the case of linear motors, like rotary motors, if an absolute position linear encoder is used, the user does not need to detect magnetic poles, if magnetic pole detection is performed once when producing a single axis, using the linear motor coils, permanent magnets, and linear encoder. Users just need to use it right away. As the manual, magnet pole detection is best down with no load. If the structure is gantry or the load is heavy or tilted to one side, such as a vertical axis, it may not be done well. When manufacturing a linear motor using the Motorcoder or an absolute position encoder, it is recommended to perform magnetic pole detection once under no-load horizontal conditions, and not perform magnetic pole detection during use. The Motorcoder is a battery-type absolute position linear encoder. However, this is an electric angle absolute position linear encoder that does not need to detect magnetic poles even if the battery is not connected. I will introduce a video of performing magnetic pole detection according to the process in the Mitsubishi Linear Servo Manual. First, among the linear servo motor magnetic pole detection methods, select the default setting value, magnetic pole detection at first servo turn on, then turn the power off and then on. Second, when I run a test drive, magnet pole detection is performed first. When I press yes, magnet pole detection is started. The motor moves back and forth while making electrical noise. Magnet pole detection is complete. Third, I change the speed to 100 mm per second and drive the motor in the forward and reverse directions to check whether the magnetic pole detection is successful. I move the linear motor shortly by 65,536 counts, which is one cycle of the magnet pole pair. And I check it by moving the 300,000 counts. Fourth, I set it to no magnet pole detection so that magnet pole detection will not be performed from now on. Fifth, I clicked on the magnet pole detection information and confirmed that the lower 4 nibbles of the magnet pole position were 3EF3. In the encoder information comparison, you see the top 4 nibbles are FFFF and the bottom 4 nibbles are around 6E1E. Turn the power off and then on. First, if you click on the magnetic pole information, the lower 4 are 3F3, the same as before turning off the power. Even if you turn the power off and on, the magnet pole information is stored in the servo drive and does not change. Second, the motorcoder senses one cycle of the pole pair of the linear motor magnet with 16-bit resolution, so data 2 is the current absolute position of the coil and magnet. If you look at the encoder information, 4 nibbles in the current position are approximately 6 cca. The current position has changed slightly as the linear motor is turned off and moves, but you can see that the lower 4 nibbles at the current position are not initialized to 0, and sensed well even though the encoder power is turned off and on. The motorcoder can sense the absolute position of 16-bit data, the lower 4 nibbles, to determine the magnetic pole position even without connecting the battery. If it was an incremental encoder when you turn it off and on, the current position is initialized to 0 and the magnetic pole position cannot be determined. You cannot drive it immediately. I'll turn it off and on again and drive it right away. By the stored magnet pole information and the sensed current 16-bit absolute position, I can drive it without performing magnetic pole detection even when the power is turned off and on. Let's drive a linear motor at 300 mm per second with a moving distance of 300,000 counts. When using a motorcoder, you can confirm that you can drive a linear motor well without magnetic pole detection. In the next video, I will explain in detail what magnetic pole detection is, and why motorcoders do not need magnetic pole detection. The motorcoder senses the absolute position and transmits the position data through serial communication. The motorcoder senses an absolute position, so it does not lose position. It is very resistant to noise because it uses serial communication. You can see that the linear motor is controlled well during acceleration and deceleration. To summarize once again, the motorcoder is a product suitable for long-distance position control-based applications such as automation equipment, transportation equipment, and logistics equipment rather than applications such as scanning equipment. If you turn on notifications, it will be more convenient when you watch the following video. Thank you for watching. SensorLab.